Okay, so I think we'll probably get started. So today we're going to be talking about semi-supervised learning some more. And in particular, we're going to look at these two graph-based algorithms that Nina mentioned in class but didn't talk about the details of. And I guess at the end, we'll also see just a little bit about active learning. One of these methods has like a nice active learning extension. And so last time I was using the chalkboard, and I found it was taking a really long time to get through material, so I made slides this time. Because we have a lot of content to cover, but I think it should be good. So, so we're going to start by just reviewing what semi-supervised learning is and when we expect it to help us. And then we're going to talk about these two algorithms. One is called graph min-cut, and the other is called harmonic energy minimization. And both names sound kind of intense, but the intuitive ideas behind the algorithms are really simple. And they get their names from the algorithms that they use to actually compute certain quantities. And so the thing I want you to take from the recitation is like mostly the motivation for the algorithms and that there exist efficient implementations, but it's not super important that you have the details of how to implement them. So we'll talk about graph min-cut and harmonic energy minimization. And then we'll look at an extension of harmonic energy minimization that lets you do active learning. So when you get a query an expert for labels for new points. And if there's time after, we can have questions either about the topics now or for the homework or projects. So, okay, so just to remind you, in the semi-supervised framework, we're still in this like pack setting, where you have some data distribution D, which tells you how likely you are to observe different input feature vectors, like how likely different x's are. And there's some true labeling function C star that we don't know. And this is a map that takes as input feature vectors and spits out class labels. So just for a concrete example, you can imagine that the data distribution is a distribution over images. And then C star is a function that maps an image to like an English word that describes what's in it. And the way our learning algorithm gets its data is first we draw an IID sample from the data distribution, and we give that to the expert. And then the expert goes and it somehow knows this true labeling function, and so it labels each of the examples for us. And then sends to the algorithm a bunch of pairs of samples of input feature vectors together with the labels that they're assigned. And if we stopped here, this would be just regular supervised learning, right? So you just have some set of examples of inputs and outputs, and you try to learn a function that sort of closely fits those. But in semi-supervised learning, we also get an additional sample of purely unlabeled data. So this just comes directly from the data distribution, but we never ask the expert to label it. And the reason why we don't ask the expert to label it is because that might be time-consuming or expensive. So we might have access to a lot of unlabeled data, but we want to avoid sort of having someone sit down and label it all. And so just for notation, I'm going to use m sub l to denote the number of labeled examples that we have, m sub u to denote the number of labeled examples, and m is just going to be the total number of examples. So typically also, ml is a much smaller number than mu. You have a lot more unlabeled data than labeled data. Okay, and so then the next thing that we talked about in class was when does unlabeled data actually help you? And if you think about it, the unlabeled data only tells you something about the data distribution, right? So if I see a lot of examples in one region of the space, that tells me, oh, there's high probability here. And if some other region of the space is empty, that means that the data distribution has no probability there. But that's a bit unsettling because we actually care about estimating the target function C, which is a relationship between inputs and their labels, right? So this is kind of a discrepancy between what we have access to and what we'd like to estimate. And so for semi-supervised learning to be successful, we need for there to be some relationship between the data distribution D and the true label function C star. And so we saw a couple of different ways of making this relationship, or making assumptions about that relationship in class. So the simplest one was this large margin separating assumption. So there we assume that the data had a linear separator, and moreover that linear separator had a margin gamma. And so if you think about what that means, is it says that there's some linear separator, and on all the positive examples are on one side and all the negative examples are on the other side. But more than that, you know that there's like a band of width 2 gamma on either side of that linear separator, so that you'll never see an example there. And so that means that the data distribution can't put any probability mass on that margin. So this gives you a relationship between D and C star. We also had a couple of other ones about like having multiple views and having like each view be independent of the other given the class label. But today what we're going to assume is that if you have two similar points, and we're going to be really concrete about how we measure similarity, but for now just at a high level, if you have two similar points, they should have the same label. So can you see why this is a relationship between the data distribution and the true labeling function? you think of like how the distribution is constrained if we make this assumption? So I guess it's not, so it constrains what the data distribution is allowed to do, right? So if the labeling function C star gives different labels to nearby points in the instance space, it must be true that the data distribution doesn't put any weight there. Because if it did, then we could see examples where our assumption was being violated. So somehow this is a bit like a margin condition, but it's a little bit weaker and more probabilistic. But the intuitive idea here is that somehow the data distribution separates the classes from one another, according to however we're going to measure similarity. So are there any questions until this point? No? Cool. So both algorithms that we're going to talk about follow like exactly the same general strategy. And so what we're going to do is we're going to try to come up with like a formal way of describing that high-level assumption that similar points should have similar labels. And then once we have sort of like a formal way of talking about this, we can design algorithms that can compute labelings for data points that sort of do the best job at satisfying those assumptions. So the first thing is we're going to need to fix some way of measuring similarities. So we suppose that we have a similarity function S that takes in a pair of input vectors, and it tells you how similar they are. So it's a big number if they're very similar, and it's going to be a small number if they're different. And so like an example of a similarity function here would be like radial basis functions. So you could take the distance between the 2 points and then take e to the minus that. So you have to do a little bit of a trick to make it so it's big when they're close and small when they're far away. But so once we have that similarity function, we're going to construct a graph where the nodes of the graph are inputs, x1 through xm. And so this contains both the labeled examples and the unlabeled ones. So in this sort of toy picture, we have 2 labeled examples, one positive and one negative. And then there's 2 unlabeled data points in the top right and the bottom left. And we're going to go and we're going to add a bunch of edges to this graph. And it's going to be a weighted graph. And the edge between any pair of nodes is going to be weighted just by the similarity of those two data points. So in this example, I've used like thicker lines to denote high weights and thin lines to denote small weights. And so the 2 nodes on the top there have high similarity, and the 2 nodes on the bottom have high similarity. But for any other pair of nodes, they have low similarity because they have these little tiny skinny lines. Okay, and then what our goal is going to be is we want to find a labeling for the unlabeled data points. So we're going to try to substitute in the labels so that the new labeling respects our like similar points have the same label intuition. So somehow in this example, it seems like the top unlabeled node should be a plus because it's very similar to a positive example, and the bottom one should be negative because it's very similar to a negative example. But we're going to see next sort of one way of like formalizing this kind of idea. But so are there questions about how this graph is constructed and what everything means? If you had, so let's say your examples x1 through xm are binary feature vectors, so they take values plus, minus, or 0 and 1. What do you think a reasonable similarity function might be? So you have two same length sequences of bits, and you want to say how similar they are.
The product?
Yeah, that would be a good idea, right? And that corresponds to counting how many bits they agree on, right? So that's one example you could use if your feature vectors had like binary inputs, and if you had continuous features, then you can use something like the radial basis function, or you could design like domain-specific similarity functions. Okay, so graph min cut is the first algorithm we're going to talk about, and it only works for binary classification. So if you want to have more classes, you can come up with a similar idea, but it's not going to be computationally efficient to compute the answers. And so what we're going to do, like the really rough idea, is that we want to assign labels to the unlabeled data, so that if you loop over or sum over the entire data set, when you look at pairs of positive examples and negative examples, after we've like added in our own labels, you want to minimize the total similarity between them. So somehow this is minimizing the amount that our assumption is violated. So I'm going to look at every positive example, and I'm going to compare it with every negative example. And if all of those similarities are small, then I've done a good job. But if one of them has a really high similarity, that means that somehow I'm violating my assumptions. Because I'll have found 2 data points that have different labels, but they're very similar to one another. Does that make sense? Yeah? Okay, and so now we're going to sort of think of a way to express this idea in terms of graph properties and things that we know how to compute about graphs. So the rest of the talk is sort of like how to express this idea in terms of graph theory and then algorithms for computing this thing. So I guess the word cut in the name min cut comes from this idea of graph cuts. And so graph cut is really simple. You just take the nodes in your graph and you separate them into two groups. And then so in these examples, there's three different graph cuts for the same graph. And in each case, the nodes in the green boxes are in one group, and then the nodes that are outside are the other group. And then you can define the weight of a cut to be the total weight of the edges that pass from one group into the other. And so like the way I like to think about this is if you kind of just imagine grabbing the graph and like pulling one group off to one side and the other group off to the other side, you're going to have some band or bundle of edges that kind of run through the middle. And the weight of the cut is like how many you'd have to cut through if you were to separate them. So there's one more property about graph cuts that's kind of important. So if we have two special distinguished nodes, S and T, which usually stand for the source and the sink, then you call a cut an ST cut if S and T belong to different groups. So somehow this cut is separating S from T. So in these examples, if S and T are the diagonal nodes, then in the first one, it's an ST cut. The second one is an ST cut again, because S and T are in separate sets. But in this last one here, since S and T are both in the green rectangle, it's not an ST cut. So if thick edges represent high weight edges and thin edges represent low weight edges, which of these two cuts has a higher weight? The first one has the higher weight, right? Because it cuts through these two thick edges. You can kind of imagine like if you pulled them apart, you'd have to cut them. Whereas in the second one, the thick edges stay within their own groups. So using the idea of graph cuts, can you think of a way of expressing the condition that we had before where we want to label all the nodes as either positive or negative so that if I looked at any pair of, or if I summed over the pairs of positive and negative examples, the similarity would be minimized. Can you think of a way maybe that you could do this with graph cuts or like express that condition? Mm-hmm. Right. Yeah, right, exactly. Yeah. So that's exactly the idea. There's like one small trick that you have to do to sort of set it up so that everything works out nicely, but like that's the idea. So the idea is we're going to try to set the graph up so that if you find a minimum weight cut with one extra property, that the two groups that you find in this minimum weight cut are going to correspond to the positive labels and the negative labels. And so we'll go through that construction now. So this is the graph cut algorithm. And so what we're going to do is we're going to add in two extra nodes. So one of them is meant to encode like positive labels, and the other is meant to encode negative labels. And I've erased the plus and minus here just because when we talked about cuts, the label of a node never showed up anywhere, right? So we want to try to encode everything in terms of only the edges in the graph. And then what we're going to do is we're going to add an infinite weight edge between any positive example and this VP node, which was supposed to encode positive labelings. And similarly, we're going to add an infinite edge between every negative labeled node and Vn. So in this case, the top left node was positive, and the bottom left node was, bottom right node was negative. So we just added in these two edges, and I made them red to sort of imply that you can't cut them because they have infinite weight. So, okay, and then what we're going to do is we're just going to find a minimum weight VP Vn cut of the graph. And so we can unpack what that means first, just really quickly. So a VP Vn cut is one where one group of nodes contains VP and the other group of nodes contains Vn. So you could think of that as being like, let's assign some subset of the nodes to be positive and some subset to be negative. We'll know which is which based on which contains VP and which one doesn't. And then so of all the VP Vn cuts, because there's going to be many of them, we want to find the one that has the minimum weight. So this is exactly what you suggested. And then once you have that, we'll just mark all the nodes in the same group as VP as being positive and all the nodes that are in the other group as being negative. So for now, we're just going to suppose that you can actually find these minimum weight cuts efficiently. We're going to talk a little bit more about it later, but for now, just like there's a polynomial time algorithm to do it. But we can talk about what are the properties of the minimum cut of this graph. So the first one that I claim is that every positively labeled point will, so the points had some original labels before we like filled in the unlabeled ones. And so any point that was originally labeled as positive, I claim that it will be in the same group as VP. Do you guys see why?
Because they are linked to V.
Right. And the edge that connected them had infinite weight. So any cut that separates one of the originally positive nodes from VP will have infinite weight. And then the only thing you need to convince yourself is that there exists at least one cut that doesn't have infinite weight. And the easy way to do that is just to put all of the positive nodes with VP, all the negative nodes with VN, and then assign the rest of the nodes to whichever you want, and that'll have finite weight. So that's good. It's sort of consistent with our original labeling. It'd be concerning if it wasn't. And then similarly, every negatively labeled point will be in the negative group, just for exactly the same reason. And so then the last thing I want to say is that now this minimum cut, so if you label the points this way, you're actually minimizing the total similarity between points that have different labels, which was our original goal in the beginning. So I was going to ask if you guys saw why that was true, but I guess it's pretty clear. Okay, so then the last thing is, how do you actually find these minimum weight cuts? So if you had an algorithm for doing that, then I could give you some set of labeled data, some set of unlabeled data. You could go in and you could fill in all of the labeled data, or fill in labels for all the unlabeled data so that it sort of fit with your assumptions the best. That would maybe be a reasonable thing. And then you could like run the supervised learning algorithm on top of that if you wanted to. And so we're not going to talk too much about this, because you could spend probably the entire hour talking about it if you wanted to. But so there's a related problem called max flow, where so you imagine, so let's say we're going to call VP the source, and we're going to call VN the sink. And you can imagine that I have a bunch of pipes that hook all these nodes together, and that the pipes have capacity that's equal to their weight. So I can push more water through a high capacity pipe than I can through a low capacity pipe. And then the question is, how much water can I pump from VP to VN? And you're looking for a rate, so how much per minute or something like that. And so when you're, so in this graph, everything is undirected, but when your graph is a directed acyclic graph, there are super simple dynamic programming algorithms for this. And even when it's not a DAG, you can, they're good algorithms. So there's this augmenting path algorithm, and then there's a whole bunch. This is, yeah. Right. So anyways, it turns out that there's a duality between the min-cut problem that we're talking about and this maximum flow problem. And it means that if you can solve the max flow problem, then you can take that solution and it gives you a solution for the min-cut problem. So since we have good algorithms for max flow, you can use those to find minimum cuts. And then another strategy you could use if you didn't like this is it turns out that both max flow and min-cut are going to be linear programs. And in fact, they're dual linear programs, which is where the name comes from. And you could just apply like linear program solver to each of these, and that would be another strategy. So are there questions about that? I mean, I guess there's not very many details, but just like high-level ideas. OK, so that's actually basically all there is to the graph min-cut algorithm. So just like to summarize, so we came up with a way of expressing our high-level intuition about similar points having similar labels in terms of graph cuts. And then we talked about how if you, yeah? Sorry? Internal flows? Yeah, right. So I guess you might need some conditions, like the similarity functions are like non-negative. Yeah, there could be some conditions, but I think they're satisfied often. If they're not egregious? Oh, not integers, right. Yeah, right. So if they're not integral, then, so you can still solve the problem. So if they're rational numbers, for example, you could find the common denominator for them all and then like scale them, and then they would be integers. You could solve that problem instead. So if they're rational numbers, you can multiply them all by some number so that they all become integers. And if they're arbitrary real numbers, I can't remember, but I think there are still algorithms. Yeah. So I think for sure, if you took the linear programming approach, then it would be no problem. Yeah.
So
yeah.
for this method, we first need to calculate the similarity between every two pairs. So it's the time complexity is n squared.
Yeah.
So that's
Yeah, right. So n squared is pretty expensive. And I think actually computing the min-cut is think it's like n cubed. Does that sound right? But yeah, so it's computationally expensive. So if you're going to do this with like some huge data set, like if you had like millions and millions of data points, like more than you could label, then you might want to come up with like an efficient approximation. I know that there's also, so I think there's no way you'll avoid getting like n squared space or m squared space because you have to store like your adjacency matrix or whatever. But I think in like the late 90s there was like a big push to come up with more efficient algorithms for these things. But okay, are there more questions? Yeah. Yeah, so it's a bit weird. So in SVM, you're trying to maximize the margin, right? And here somehow my data points don't even need to be in like a vector space. So it might not make sense to talk about like linear decision boundaries and things like that. Right. So to solve the SVM problem, you have to solve a quadratic program. And in this case, it's a linear program. Yeah. Yeah. Okay. Are there any more questions? Yeah, actually, it's a really good point that it's hard to do if you have a lot of data points. It's an advantage of the next algorithm because there's a way of implementing it that doesn't require you to actually, like, if you want to know the label for a single point, you can compute that independently of the rest of the points, and that's going to give you a bit more efficiency. Okay, so now the next algorithm that we're going to talk about is called harmonic energy minimization. And so the idea here is really similar, except we're going to relax the condition that we give a hard labeling to the data points. So instead of requiring that each data point is either positive or negative, we're going to allow soft labelings, which is just going to be numbers between 0 and 1. And so a value of 1 sort of represents I'm very confident that this is a positive example. And a value of 0 represents like I'm very confident that this is a negative example. And 0.5 would be sort of you're not sure. And then we're going to come up with a similar way of formalizing this idea of finding a labeling of the data points that sort of violates our constraints the least. And then we'll look at how to solve that problem and then sort of see what it means intuitively. So this, again, for soft labelings. So I've just put the same graph here. It's kind of hard to tell. These are supposed to be different shades of gray, but the bottom two ones look totally black. But so the idea in the soft labeling is that you might take your unlabeled examples and give them a number between 0 and 1. And so in this case, you might think that since the top right example is close to a positive example, it should be close to 1, but it's also somewhat connected to the other guys, so maybe you're not certain that it should be positive. And similarly for the bottom left corner. And so usually you can think about the labeling, the numbers in your labeling as being sort of a confidence parameter. So if it's 1, you're certain it's a positive example. If it's 0, you're certain it's negative. And if it's like 50, 0.5, then you sort of don't really have a good guess. And the reasons for using soft labelings are it's computationally tractable if you have more than 2 classes. So if you try to extend the idea from the last algorithm, where you're going to find instead of like a cut that separates into 2 groups, you could also look for a cut that separates it into three groups and minimizes the total edges cut by any sort of edge boundary. But it turns out that those problems become NP hard after 2. So in this case, it turns out that you can still, at least in polynomial time, find the minimizing soft labeling. And it's also sometimes useful to have a measure of confidence, right? So sometimes you'd like to know if your algorithm is very confident that the label should be 1, or if it's very confident that it should be negative. So you don't if it's not confident and it just says, oh, well, I don't really know, so it's 1. That's like a good chance for you to make some potentially dangerous mistakes. And then if you wanted a hard labeling, as long as you don't care too much about guarantees, then you could always get one just by hard thresholding the soft labels. So if it's 0.5 or bigger, then you set it to 1, and if it's smaller than 0.5, you set it to negative. Or yeah. Are
we still assuming the similarity function?
Yeah. So we're still going to use a similarity function to construct this graph. And now the difference is that we're going to, instead of trying to find a hard labeling, we're going to look for these soft labelings. One other thing that's maybe worth mentioning is, so I have been kind of implicitly assuming that the similarity function is symmetric, just because these are undirected graphs. But in both cases, lots of things can be generalized to the case when the similarity function is not symmetric. Okay, and so now, fortunately, this algorithm is just a bit more technical to explain, but it's really not so bad. So last time we had this idea of minimizing the total similarity between points that had different labels. What we're going to do instead this time is we're going to try to find a function, which is a mapping from our examples to the real line. And really, it should be constrained to 0, 1, but we're not going to enforce that for now. And we want that function to minimize this objective here, E of f, which is just summing over all pairs of examples. And then it's looking at the square difference between their labels. And then it's weighting that by their similarity. So if you have two examples that are very similar, the similarity function will be high number. And so their squared error is contributing a lot to this error term. Whereas if you have two examples that have extremely small similarity, then they contribute almost nothing, even if their labels are different. So this is a different way of formalizing this idea that similar points should have similar labels, because we're going to penalize them based on the product of sort of how different they are and how similar they were. And then we're also going to need a constraint that says that for all of the points that we actually know the labels, that function should give 1 for the positive examples and 0 for the negative examples. Okay, and so I guess this function is typically called an energy function, and this comes from some connections to other disciplines. So I guess in chemistry, you might think of the energy function as measuring the energy in like a configuration of atoms. And then the steady state is typically the one that has like the lowest energy. And so this energy minimization problem, I guess, has analogies to these areas, but I don't know very much about it. But are there any questions about sort of just the general goal here? So we want to find a labeling so that that minimizes this energy function subject to those constraints. Yeah. Yeah. Yeah, right. So if you really needed like hard labels, like either positive or negative, then you do this thresholding. But yeah, one way of thinking about it, so just thinking about the numerical value that you get, you can think of it as being a probability, like describing the algorithm's belief. So it's like 90% sure that this label is positive and 10% sure that it's negative. But we'll see that in this particular example, there is another way of interpreting what the probabilities mean in sort of a more concrete way. That's a lot easier to understand. But we'll get there in a minute. But so the general goal is clear. We want to find some labeling that agrees with the labels that we know. And on all the other labels, it sort of minimizes this energy function, which is capturing how much it disagrees. Yeah.
So what is the upper bound and lower bound of the similarity function?
So for this part, you're actually going to need that it is non-negative. The paper, so at the end, there's 3 papers that talk about this. And they don't explicitly say it, but I'm pretty sure you need, that's a requirement.
So this Sij is always greater than 0.
Yeah.
So then if you want to minimize this function, then the fi will equal to fj.
Mm-hmm. So you would do that, except there's also constraints, right? So for the point that you have the labels for, they have to be set to their original value. So some labels have to have fj equal to 1, and some have to have fj equal to 0. And then in the middle, they should be trying to minimize the... Yeah, so it's only an interesting problem because of the constraints. If you didn't have the constraints, you could just set them all to be 1, all to be 0, or all to be like any constant. And then you get like a perfect score. That's a good question. And as far as upper bounds, I'm not sure. So you might require that the similarities are bounded. But the only way that they wouldn't be, since you have finitely many data points, is if the similarity could be infinity. And then it probably works out, but you might need to be careful. So. Okay, so now the next thing that we're going to talk about are just some properties of the minimizer of that energy function, subject to the constraints. And so this isn't super important. You don't really need to know about it, but it's the reason why we have efficient algorithms for this problem, and it's also where the name comes from. So I thought it was worth mentioning. But so it turns out that the solution to that problem is always going to be what's called a harmonic function. Okay, what a harmonic function is, it's one that satisfies the constraints or like the boundary conditions, and then for every other point, the function value at j, so suppose j is some unlabeled data point, the function value at j needs to be a weighted average of j's neighbors, the function value at j's neighbors. And the weights are going to be the similarities. And if you look at this dj, it's called the weighted degree of node j. And it's just the sum of the edge weights going out of node j. Okay, so if you look at the equation on the left-hand side, you have like an fj on one side, and then there's like a sum over fi's on the other side, right? And so it turns out this is a fixed point equation, and you can use this. It's like the basis for both like the theoretical derivation of some algorithms, and it's also like you can actually solve this problem by iterating this update. So you start with some arbitrary function, and then you loop through the states, and each time you set each one to be the average of its neighbors. And turns out that this will converge to the minimizer of the original problem. But so I mostly brought this up because it's where the name comes from, and it's the reason why you have efficient algorithms. So, right. And so now there's another way of interpreting what the energy minimizing function is, and I think this is the intuitive version of the algorithm that you should have in your mind all the time. It's I think it makes it a lot clearer what's going on. So I've just copied the toy problem that we've been working with for a while, and so we have this one positive example in the top left and the negative example in the bottom right, and we're just going to ignore the numbers for now. So imagine that you have a particle that's doing a random walk on this graph. So it starts at some node, and then it picks an edge randomly and it follows that edge, picks another edge randomly, it follows that edge, picks another one, goes on. And suppose that it chooses edges with probability that are proportional to the weight of the edge. And this is where we require that the weights be non-negative. Otherwise, that won't form a probability distribution even after you normalize it. But so suppose that you have this particle that sort of bounces around, and it's more likely to follow thick edges than it is to follow thin edges. So you might, yeah. So then what the energy minimizing function is, like the labeling that we're looking for, it tells us exactly the probability that that random walker, if you started it from a given node, will hit a positive label before it hits a negative label. So in this example, supposing that this was the labeling that minimizes that energy function, what that would tell us is that if you started a random walk in the top right corner, and then you followed edges with probability proportional to their edge weight, then with 90% probability you would hit the positive sign before you hit the negative sign. And for the node in the bottom left corner, with 90% probability you would hit the negative sign before you hit the positive sign. So the way you would prove this is if you come back to this slide. So here, if you look at fj, if you sort of pull the dj in underneath the similarity function, those are going to be a bunch of non-negative numbers that sum to 1, as long as they're not all 0, I guess. And then they end up looking like probabilities over the neighbors of j. And if you sort of take that and sort of work with it a little bit, you can get to this interpretation. Again, so this also gives, so coming back to the computational problem. So one thing that's really hard is like, let's say you have like 1 million data points. Then to even store this graph explicitly, you have to store like a 1 million by 1 million table, unless like maybe you have some sparsity or something like that. But you might be able to just sort of on the fly compute the similarity between two different points. There's no real need to pre-compute them all and put them in a table. And if you take this random walk point of view seriously, it gives you a way of actually estimating the label for a point, right? So you could start a random walk at some label at some point that you want to know the label for, and then you'd like loop through your entire state space. You compute the edge weight for every other point. Then you normalize them, you take a random step, and you do that over and over again until you hit either a positive example or a negative example. And that gives you sort of one sample from a binomial distribution whose parameter is the probability of hitting a positive example. And so you could do that many times, and you could use like the maximum likelihood estimate, like just average them. So if you did like 1 million of those random walks, and you counted what portion of the walks hit a positive sign instead of a negative one, that would be an unbiased estimate of this label. So you can imagine you can use this to sort of more efficiently compute these labels in situations where each point is close to labeled examples. So there's a good chance that you're going to hit one very early on before sort of taking too many steps. But it's only useful if you want to estimate just like a subset of the labels, right? Because if you wanted to estimate all of them, then you're going to end up doing this sort of linear time process for each point, and then you're back into n squared computational complexity. So the other thing that's nice about this is it kind of gives you some more intuition behind what this is kind of doing. So in some sense, it's computing a nearest neighbor style algorithm where distances are being measured sort of along the surface of the graph that you created. So if you imagine that your data points are sort of scattered in space and they sort of form like some lower dimensional manifold, these random walks are sort of doing, sort of just like walking uniformly around on the surface of this thing. And so somehow this is respecting like the data's intrinsic sort of geometrical properties. Yeah. Mm-hmm. Mm-hmm. Right.
And when you do the sampling, you to do the SCMC sampling many times,
Mm-hmm.
get the result of
Yeah, right.
I don't know. I just guess.
Right. So you need to be a little bit careful to make sure that the amount of time it takes for you to hit a positive label is finite. And you can imagine you have. Oh yeah, sure. So you need to be careful to make sure that if you're going to do one of these random walks until you hit a positive or a negative example, you need to make sure that happens in a finite amount of time. So you could construct graphs where it wouldn't happen, right? If there was like a loop with no labeled examples and no weights going outside, if you started a random walk there, you just stay in the loop forever, right? So you need to make sure that doesn't happen. And I guess there would be some mild conditions on the similarity function that would guarantee that. If you look at the stochastic process that you get, it's called a Markov chain. And you'll have, everything will work out if the Markov chain is a single recurrent class, which is, I guess, means that with non-zero probability, you go from any node to any other node. And if that property is true, then all these random walks will stop in finite time. But it could still be long. Like if your data is sort of nasty, it could be a really long time. Yeah. So it's only going to be more efficient if you have like lots of labeled points near all the points that you care about. So you hit one of them sort of early on.
So it's really sensitive to
Well, so the running time depends on sort of how well distributed your labeled examples are. And the number of random walks that you need to do, I think, doesn't matter so much. So you have like the variance drops like 1 over square root of n or something like that. Yeah, no problem. So are there any more questions about this like random walk interpretation? Is it? Yeah.
I actually don't get the equation like that. So what's the significance of taking a positive example before a negative one?
Yeah, right. So imagine that you're a point and you're very near to a lot of positive examples and far away from all the negative examples. Then it seems more likely that you're going to run into the positive ones before the distant negative ones, right? And so the idea is somehow the probability that you hit the positive examples is some way of measuring sort of how far away they are. And so then the labels here are sort of telling you, I'm going to say that you're, yeah, so the label is somehow saying like, are you closer to the positive examples or closer to the negative examples? Does that make it any clearer or no?
So what if I take a negative example? What does it mean?
So one particular random walk maybe doesn't tell you very much because you could get unlucky and hit a negative example, right? But so it's like on average, how many times would you hit positive examples versus negative examples? Oh yeah, sorry. I guess it was a little bit unclear. So it's the probability that you hit a point that originally had label positive or originally had label negative. So the labels you guessed are not included here. So it's like you know that some points are positive and you know that some points are negative, and then the label that you're going to guess for another point is this probability of it hitting one of those known values.
So you mean to say if I start from a positive example and then I hit a positive example soon after, whatever I traverse between those two are all positive?
So I guess you would stop the random walk once you hit either positive or negative. So if you started in a positive example, you would just stop immediately and say, I hit a positive example. And the reason why you want that to be true is because for all of the examples that were positive, like in your original labeled data set, you want to make sure that your function gives them a label of 1, right? And so this is like sort of one of these are cases where if you started in a positive example and you don't take any steps, you've already hit a positive example. So the probability of hitting a positive example is 1. And if you were to go like one step away, then there would be a really good chance that you would sort of step back and hit it again. Or you might sort of go off and hit one of the negative samples. Sure. We can also talk about it after if you want. OK, so now the next slide is just there's sort of a matrix technique you can use for computing that labeling without doing this random walk procedure. And if you were to derive this, it comes again from that fixed point equation and writing things out a little bit differently. But so we'll let W be the m by m matrix of similarities. So we're going to order our data points 1 through m. We're going to put all the labeled samples first. So the first L things will be the labeled data points, and the second U, or like M sub U, I guess, examples will be the unlabeled data points. And this W matrix, the ijth entry, is just the similarity between examples I and j. And then we'll let D be the diagonal matrix, where the diagonal entries are the these like weighted node degrees. So it's just the sum. So Di is going to be the sum of the ith row of W. So you can just define these matrices. These are things that you know if you can compute the similarity function. And then we're going to decompose W and D into this like block form, where we have one component that's just sort of for the labeled data, one component that's just for the unlabeled data, and then these like off-diagonal blocks that sort of talk about the relationship between the two. And we'll do that for both W and D. And then similarly, we're going to take our function, our labeling function, and we're going to decompose it as the labels for the originally labeled data, so the data that came from our labeled set, and the unlabeled ones. And so one thing here is that you can represent these functions as vectors, m-dimensional vectors, right? So, okay, so with all these definitions, it turns out that the unlabeled labels can be written as a linear function of the labeled data, and it's just given by this expression. So FL, we know that it has to agree with the labels that we observed, so we know the values for FL. And then FU can be computed from FL and these W and D matrices this way. So it's not super important. If you want to like implement this stuff on like toy examples, you could use this. And if you want to prove that this works, you would go back to that fixed point equation and derive it from there. So other questions about this? Yeah.
This, like D, what did subscripts mean?
Yeah, right. So I guess, can you see the mouse? No. So WLL. So if you imagine this matrix, it's an M by M matrix. And M was the sum of the number of labeled points we had and the number of unlabeled points. And so WLL is like the block of that matrix in the top left corner that has only the indices of the labeled data points. And then like WL has like the unlabeled ones on one side and the labeled ones on the other side. Yeah. Cool. Okay, so just to summarize, so the really major difference between this and the graph min-cut was that here we allowed soft labelings, and kind of did that for two reasons. So one is that you can generalize this more easily to when you have more than two classes. And the second reason was that if you have some notion of confidence, this can be kind of a useful thing. Then we had this like quadratic energy function that was trying to capture this notion of similar points having similar labels. And then we talked about the properties of the energy minimizing labeling, and then just sort of said that there was this efficient matrix method for computing the function when you have those matrices in hand, and the computational power to invert them. Actually, so are there any more questions about either of the two algorithms? Because now we're going to talk about something a bit different. And okay. So now we're going to talk about how you can do active learning with this energy minimizing or harmonic energy minimization algorithm. So just to recap again, so in active learning, the situation is that the learning algorithm is just given a bunch of unlabeled data. And then its goal is still to try to approximate the true labeling function C star. But rather than having some random data points being labeled for it, it can actually send a label to the expert and say, will you please label this? And then the expert responds with the label. And so the learning algorithm wants to, primarily they want to get a good estimate of C star, so they should solve the actual problem. But they also want to minimize the number of queries that they make. And so we saw in class a couple of examples where you could get away with exponentially fewer queries, but I guess it's kind of a rare situation. And so the algorithm that we're going to talk about today sort of extends this harmonic energy minimization algorithm to the active learning setting. And it's a heuristic algorithm, so it's kind of hard to prove things about it, but it makes a lot of sense intuitively, and I guess works well in practice. And so the paper for this was actually published the same year as the original paper. But so suppose that I gave you some data set. You had some labels in it. So maybe in the active learning setting, you've already requested a couple of labels. And so you have some labeled data and some unlabeled data. And you compute the labeling that minimizes that energy function subject to the constraints that it agrees with the labels that you know. And then you're going to try to pick one point to query the expert for. Say, will you please give me the label for this point? And so one really simple idea would be to query the label that has the label closest to 0.5. So this is the one where you're the most unsure about its label. And so you'd say, in this case, you would pick the middle one. You'd ask the expert for the label, it would give it back, and then you'd have 0 uncertainty there. So in some sense, you've reduced your amount of, like your total amount of uncertainty. And that would also improve your knowledge for the other 2 unlabeled data points, because now you have a new labeled example. So you get the label, and then you'd recompute the error energy minimizing labeling. But so do you guys think that this is a good idea? Should you do this in practice? And so in this picture, it's a bit misleading, because here it's a good idea. But you can have sort of a slightly different situation. So, so on the left-hand side, you have the original graph, and the minimum weight is 0.5 in the center. And on the right-hand side, I've added a bunch of nodes that were more certain in their label. They should be 0.6. And I've excluded a lot of edges because I gave them similarity 0. And there's a slightly stronger edge on top and a slightly weaker edge on the bottom, which is why this guy has weight 0.6. And then he's strongly connected to all these other guys. And they should, if you think about it, they should really all have the same label, or at least very similar labels. I think it should actually be exactly the same, though. So now, if you imagine, if you query the expert for the label of the 0.5 guy, he's going to tell you a little bit about, well, you'll get the label for that node, and you'll learn a little bit about its neighbors, but it's not going to tell you very much about this big cluster where you're not sure what's going on. And maybe a more reasonable idea would be to query the roots of this like sort of short tree on the right-hand side. Because if you learn the label of that node, its uncertainty is going to go to 0. And since all these other guys only depend on it, they're also going to go to 0. So the total amount of uncertainty that you would reduce by picking this sort of root node is better than if you picked 0.5. Does that make sense? So it's like if I learned the label of the roots of that tree-shaped thing, it would tell me a lot more actually about more nodes than learning the label of 0.5, even though 0.5 is less certain than it. So we want to come up with another heuristic that somehow would know to choose 0.6 instead. And so this ends up being sort of, so it's totally heuristic, and it's a little bit complicated to write down, but it's a really simple idea. And so actually just going back to this picture, basically what it amounts to is it says, for each node that I don't know the label of, let's imagine that I got the label. And then you have to guess, is it going to be a 0 or a 1, but we won't worry about that. And then it just basically computes it picks the one that's going to increase or decrease the uncertainty the most over the entire graph, instead of just looking at a single node. So we can write that down formally, but I just wanted to give like the rough intuition before we do it, because it's yeah. So it makes sense, but it's just a bit confusing. So we're going to define the estimated risk of a labeling function f to be this expression on the left. And so this is actually like a really simple thing. So it says for each node in the graph, what we're going to say is, what's the probability that, so this SGN function, it's supposed to be the sign function, but it's a bit, so this is the function that takes a number, and if it's above 0.5, it sets it to 1, and if it's below 0.5, it sets it to 0. So that's maybe not the best notation, but, so it says, if I were to threshold my label at that node, what's the probability that it's equal to some random variable yi, where yi is being sampled from a binomial distribution with parameter, oh shit, not binomial, Bernoulli. That's a huge typo. But so basically you have bias coin. So what this is saying is, so for each node, imagine that the true label of that node is going to be 1 with probability fxi and 0 with probability 1 minus fxi. So I'll fix this in the slides before we post them. So this is saying my estimated risk is just the total probability, like so summing over all nodes, of the probability that my thresholded version doesn't match the thing sampled from that Bernoulli distribution. And you can rewrite this more simply as just being the minimum of fxi and 1 minus fxi. So if fxi is 0.5, then this minimum is going to be 0.5. And if it's 1 or 0, it'll be 0. And for values in the middle, it sort of scales nicely. So this is trying to capture sort of, for each individual node, how uncertain are you about its value, and then summing that quantity up over all the nodes in your graph. Okay, and so now we're going to let f with like plus xk, yk be the labeling that you would compute if you had added the label for point xk. So it's like you add in the label for this point, then you rerun the harmonic energy minimization algorithm, and it's going to give you a new labeling, and we're just going to use this notation for that labeling. Okay, and then what we're going to do is we're going to ask the expert. So ideally, we'd like to ask the expert for the for the label for point xk that minimizes the risk of f plus xk yk. But when we're choosing, we don't know what the label yk is yet. So what we're going to do actually is we're going to compute the risk if it were 0 and if it were 1, and then take the average of those with our belief probabilities that it's going to be 0 or 1. So, right, so what this corresponds to is this corresponds to the expected risk after querying for the label for point xk, where all the probabilities in the risk are actually being determined by our current labeling function. So are there questions about these definitions? But so just to go back, right, so I guess there's two things. So one is that intuitively this is trying to capture this idea of choosing labels that are going to tell you about not just its label, but points nearby. So it should maximize sort of like the total information gain. And then the second thing is that at first glance, it looks like this is going to be really computationally expensive, right? Like, so for each unlabeled data point, I'm going to have to retrain my labeling if I imagine putting in a 0 for that label and putting a 1 for that label. And I'm going to do that for every single unlabeled data point. So it seems like you're going to be solving this problem like a lot of times. But it turns out that since most of these problems overlap, like they contain basically the same matrices, there are ways of sort of combining lots of the calculation. So there are, I can't remember the exact order, but they're still polynomial time, and they're much cheaper than if you were to actually resolve every single optimization problem. And then if you were to use that heuristic to pick a label for this one, again, it's actually going to pick the right label here. So it's a bit high level, but the idea is instead of picking the node that you're the most uncertain about, pick one that's going to sort of decrease your overall uncertainty the most in this one-step look ahead. So it's kind of like a one-step greedy technique. Okay, and so these are just the papers that we're following. So the top one is about min-cut, and then the next two are both about harmonic energy minimization and doing active learning with them. So I guess, are there any questions? Any questions about the assignment or the project? So if you guys want to talk about the assignment, I can stick around for a couple of minutes afterwards, and we can do that if you'd like. Or